Okay, hello everyone. Welcome to the 31st Surface Ventures keynote webinar. Great to see some of you already typing hello in the chat. For those of you that haven't yet, you can just say hi and tell us where you're joining from today, just to check that we're coming through loud and clear. My name is Dr. Sam McMaster. I'm the event manager here at Surface Ventures, and we are a non-for-profit organization. Our mission is to provide world-class materials science education for academia and industry. Today, it is my pleasure to introduce Professor Andres Fabian Lasagni of Technical University of Dresden. So Andres is a professor at Technical University of Dresden since 2012 and the director of the Center of Advanced Microphotonics since 2017. His research focuses on laser-based fabrication of functionalized surfaces and high throughput laser texturing. He's authored over 300 articles, holds 30 patents, and has received multiple awards, including the Werner Koster Prize, German High-Tech Champion, and Materials and Science Technology Prize. Okay, for those of you that may have some issues with the sound, could I just ask you to please refresh your web browsers? This should fix any issues. Okay, and many thanks to today's partner, Pulsate. We'll have a short presentation from them later in the event. As we go along today, please type your questions into the chat and they will be marked for the Q&A session at the end. We're planning to go for around 60 minutes in total today, and we'll be sharing a link for your attendance certificates later in the event. So let's welcome our speaker to the stage.
I hope you can see and hear me.
Yes, we can. Excellent.
Thanks a lot, Sam, for the invitation, for being today here in this webinar. And so I imagine I can start.
Yes, please. If you, I'll just stay on stage for a moment to check that the screen share is working, and then I'll leave stage and let you present.
So now I hope then you can see the screen and.
Excellent. Yes, I can.
Perfect.
All right.
Okay, so then I start. So I am Andres Lasagni from the Technical University of Dresden and also from Fraunhofer AWS. And what I want to present today is how we can create or enhance functionalities on technical relevant surfaces using laser-based manufacturing methods. And before I start, let's tell me a little about my chair. So the chair for laser-based manufacturing that is based here in Dresden, Germany. And we are dealing with all topics of laser manufacturing with a strong focus on micromachining, software functionalization, but also now dealing with other topics like welding, cutting, hardening, and so on. And of course, in strong cooperation with Fraunhofer AWS that is also here in Dresden, and by the way, is part also of Pulsate project. And as some say, I am also responsible for the Center for Advanced Microphotonics, and this is a cooperation between the TU Dresden and Fraunhofer AWS, where we bring the basic research that we mainly develop, let's say, at the TU Dresden, through industrial application, through the development of systems, machines, and equipment, as you will see also some examples today. Okay, so let me start with a motivation or an inspiration slide. Probably you have seen this or something similar in the past. By analyzing the surfaces of plants, insects, animals, it is possible to find a lot of functional surfaces, which functionalities are based not only on the surface chemistry, that's clear, you need also to control the surface chemistry, but also are based on different structural elements with feature sizes in the nanometer, submicrometer, micrometer, or sub-millimeter range. And based on these topographies or complex geometries, then we have this advanced function. Yeah? So for example, let's just look one example here in the center of the screen. This insect is also called Colemolae, has a very complex topography with structural elements going from 600 nanometers to here the larger ones. They have a separation distance about 10 micrometers. And because of this complex geometry, bacteria cannot adhere. So these insects, let's say, they survive long time because they don't get contaminated. Then there are other examples like some snakes, for instance, that also have a complex geometry, complex topographies, and this permits to decrease the friction coefficient when they are moving, for example, in the sand or in the desert. And therefore, if we just analyze the hundreds of publications that have been written in the topic, for instance, we can see, okay, if we want to control friction, so we need to produce structures with resolutions in the micrometer, submicrometer, submillimeter range, and to control biological properties, or let's say the intervention between living organisms and surfaces, then, for example, we need to make structures in the submicrometer range. So the question now is, so what we learn from the natural examples, again, if you look again all these examples, the structures are also kind of repetitive, so they are periodic or quasi-periodic. So this sounds or looks to work very well. Then in addition, we need sometimes complex geometries. That means combination of structures with structural elements with different length. And this is actually what we want to do. We want to bring this into technological relevant materials to enhance functions. And clearly, if we want to bring something into production, we have to be fast. So if we are fast, then the process costs are reduced. We need also, if we can, of course, to treat different materials with the same technology, like metals, polymers, ceramics. And it also looks that we need the combination of different scale elements, so we need to create hierarchical surfaces. And one way of doing this is using laser-based technologies. And in the slide is kind of summary what is related to the resolution of structures that are possible to fabricate, and then the throughput, so the process speed. In general, what is observed, we can see, is that when producing small feature sizes or structures with small feature sizes, then the productivity decreases. Here on top, we have some methods that are called interference patterning that already reach high throughput, but we want to be clearly in this part, let's say, of the diagram. We want to have both high resolution and high throughput, and the question is how to do that. Yeah, this is what I will try to tell you today. The advantages of laser-based methods is that we can apply them on a large variety of materials. We just need that the laser radiation is absorbed by the material we want to treat. Here we have also the advantage that we can selectively treat the areas that have to be modified at the positions where we need a special function. We don't have to treat the whole part, let's say. And also that depending on the fabrication method we use, resolution up to the submicrometer range is possible. And as I said before, the challenge is how to get resolution and throughput. So now let me introduce three standard, or not maybe so standard, but three laser-based fabrication methods that can be used today for that. The first technology, the most famous, is direct laser writing. So as the word or the name says, the idea is to, for example, to guide the laser beam using a scanner system where we have two mirrors that are moving. So we are scanning here the surface of a part, and this way we can create very complex geometries. So with the shapes that we need. we only have one limitation that is related to the resolution that we can reach. Yeah? So we have, which is so-called diffraction limit, which means that to get a very small laser spot, we need, for instance, as you can see here on this equation for Gaussian beams, we need short wavelength, we need short distance between, let's say, the lens and the surface, and we need a large initial diameter of the laser beam. So typically, with this technology, we can reach beam sizes about 20 micrometers, so between 10 30 micrometers. On the other side, also it's important to mention that the focal depth, yeah, is also decreased, so we can focus the laser radiation better, but then the focal depth or depth of focus is reduced. That means if the position between our optics and surface changes, it could be that we will be quite fast out of the focus. So another technology, and this is now special for doing textures with structures much smaller than the beam diameter and direct laser writing, is what we call direct laser interference patterning. And here the idea is just to put 2, 3, or 4 beams or more, yeah, that are combined simultaneously on the surface of a material. And when that happens, for example, let's look here the example with 2 laser beams. So we create a periodic variation of the laser intensity. This is called interference pattern. And what does it mean? We have regions in our area where we are overlapping the beams that they have high laser intensity, and regions that are dark, which means there is no laser. And therefore, then this kind of patterns, they are like a stamp, a stamp of light that you bring to your material, and you create these geometries with, for example, just using one laser pulse. And what is here important to mention is that the distance between, for example, the lines in the 2 beam configuration can be controlled by changing the intercepting angle between the laser beams. And you can go down to half of the used laser wavelength. So here an example how it works in the practice, for example, with 4 beams interference. So you have the 4 beams that are combined to the surface. If we're using Gaussian beams, I will start the video again. If we're using Gaussian beams, then we have also a Gaussian envelope, let's say, that is where the interference pattern is included. And then either we move the beams or we move the part, and we can control the separation distance between the different laser pulses that we are applying. And this way we can also enhance the homogeneity of the patterns that we are creating on the surface. So another technology that is very common today also is called laser-induced periodic sulfide structures. In this case, we are not using many beams, we are using also just one laser beam. But what we do is that, okay, we are accumulating, let's say, energy over the surface. So we are putting a certain dose of energy on the surface. And then we have some kind of self-organization mechanisms that start to develop these periodic structures. And depending on the laser parameters that we use, we can get different kind of leaps, like, for instance, low spatial frequency leaps. They have a size about the laser wavelength, or even we can create the so-called high spatial frequency leaps that they have a characteristic size that is smaller than half of the used laser wavelength. As I mentioned, the strategy, we have a laser beam and we start to scan the surface, so we have to overlap in the vertical, in the lateral direction, and depending on the energy dose that we apply and how the laser pulses are distributed, we also can create very well and homogeneous structures. Okay, so now what we also can do is to put many of these technologies together. And here there are a lot of examples of topographies that can be created using laser writing, for instance, with nanosecond pulses or picosecond pulses, interference patterns, or then interference pattern on direct laser writed surfaces. But you can see there are really a huge amount of topographies that we can create using laser-based fabrication methods. So now let's go to some application examples. And one of the most, let's say, studied properties that you can modify when using this kind of technologies is the wettability of surfaces. And there are a lot of studies, there are laws, equations that you can use for explaining the wetting characteristic of structural surfaces. And I like to show this slide because here we learn, or we can get an idea how important is maybe to create what we call hierarchical structures. So in general, let's say you have a flat surface, let's say it's a metal. Normally in a metal you have a water contact angle of about 80 70 degrees, so it looks more or less like this. So you see the droplet of water, let's say if this is water, is wetting the surface. If you have a nanostructure, then it can happen that then the what we call water contact angle, that is a characteristic of the wettability state of a liquid on a surface, increases. So let's say this water droplets start to be more spheric. You could get the same with maybe a structure that is a little bigger, but what it has been seen in many examples, also natural examples, is that the combination of both length scales is very efficient to, for instance, to repel water. So let's try to reproduce such kind of hierarchical structures on aluminium. This is an example on aluminium. And here now we have 4 different topographies. The first one is just the reference without any structure. Then we have here aluminium surface treated with direct laser writing. So the size here of this structure is about 60-70 micrometers. Then we have what we call pillar-like structure created with direct laser interference patterning. So they are about 5 micrometer in size, so the repetitive distance, and then both things together. So on top of the direct laser writing produced topographies, we put the interference patterns. So let's look what happened when we evaluate the water contact angle as function of time. This is also very well known. There are many studies that show, for example, what we also observe, that with time at the beginning, immediately after the laser treatment, the surfaces get super hydrophilic, so they wet a lot the liquid, and then with time, after certain times, like here, like 10 days, 15 days, they get super hydrophobic, which means the water is repelled. In the diagram here, we observe that the blue line is a little on top, let's say, of the single scale structures, but this is within the statistical error. So let's say they behave the same, but I will show you later some advantages of the hierarchical structure. So, okay. Important, after, let's say, some time, 10 days, everything gets hydrophobic. And here we can see in reality what does it mean. So this is the aluminium surface. We try to repeat the video. So you see that it's bouncing on the structure surface. So any possibility for the water to wet the surface. And something similar we can do in other materials. Here is in stainless steel. The laser treated area is the black area. So because we have such kind of complex topographies, the visible light is strong absorbed. And here you can see it's not just a droplet of water. We have plenty of water in this container, and there's no way for the water to wet this surface. So this looks nice. So it's working. Super hydrophobicity is is an advantage, but the question is, do we need these hierarchical topographies or not? So then we go to a new experiment now related to the fabrication of ice repellent surfaces. And what we did, I hope the videos will run. So we have here, you can see let's say the lateral image of the texture aluminum surfaces. And from the top now we are placing a droplet of water. So the video is crashing. Let's try again. Okay, now I think it's working. So from the top are the droplets of water coming. The surface is freeze, I mean, it's at minus 20 Celsius degree. And now you see how the droplet starts to freeze. And in particular, what we observe that, and this is coming now, in the case of the hierarchical structure, we need much more time to freeze the water. So here there is a clear advantage of producing the hierarchical structure. And the other was, okay, let's say in dynamics test, now we come back with our droplets, and only, you will see now in the video, only in case of the hierarchical structure with direct laser writing and interference, we have bouncing of the droplet, which means now think this is a plane, it's flying. If the water tries to adhere to the surface, it will not have a chance to attach. So therefore, yeah, so there is clearly an advantage of the hierarchical structure. So other reason why hierarchical structure are also interesting is because we can start also, let's say, to combine different functionalities. And here what we wanted to do is to see what happens if we damage the structure surface. So, and on the left side, so on the image A, we have, let's say, single-scale interference structures. So you can see here the small elements produced. And the red zone is the area that was damaged. So we have mechanical contact, and there you see we totally destroyed the topography. In case of the hierarchical structure, so we are protecting some of the small elements, let's say, because of the large craters that we produced before. And now if we look or we measure the water contact angle after this test, we will see that in case of the hierarchical structure, so we are losing some of the hydrophobic properties, but they are strongly retained. In case of the single-scale topography, the water contact angle is not written here, was much lower, so that we totally lost the functionality. So this is also the idea of combining structures. Actually, this is what nature is doing. In many cases, the big topography, let's say, the big topographical elements are used to provide mechanical stability to a specific function. So let's go with another example. This is also indirectly related to wettability. So this is the case now of self-cleaning. And let me show you this animation video from William Tillicke. So this is simulating a natural surface of a plant like the lotus leaf. And then there is some dirt on the leaf. And because the lotus leaf is super hydrophobic, so then the water is rolling, let's say, and this produces a self-cleaning process of this dirt. So the droplets of water take the dirt away from the surface. So then we decided to create an experiment trying to reproduce this property. And here you observe on an aluminum structure surface with both direct laser writing and interference patterning. So this is a high-speed video. You see how the droplet of water now is rolling on the surface. And you start to see that it's collecting all this dirt, artificial dirt, let's say, that we place on the surface of the texture aluminum material. And we try that with organic dirt, with inorganic dirt. There is a publication about that. And we could observe that the hierarchical surface also is bringing an additional improvement of the self-cleaning properties. So now let's go to another application example, which is related to more in the area of tribology. Normally in tribology, what you want to do is to reduce the friction coefficient or wear in parts that are under mechanical last, let's say. And this is also somehow connected with wettability, in particular when you are using oils. If we evaluate tribological properties in dry contact, of course, that is a different talk. Let's say there you want to reduce the contact area, you want to contain, let's say, the debris that is produced, for example, into some holes, so you can avoid further wear. But here we were evaluating how long we can enhance the lubricant lifetime over a structure that is patterned. And here we use different kind of topographies, so line-like, dot-like, and what we call cross-like or pillar-like structures. We use here quite cheap laser source, so nanosecond pulses, typical wavelengths that you can buy everywhere, so one micrometer wavelength. And then we evaluated how is the evolution of the friction coefficient in a tribometer, so a ball on disc tribometer. So in a ball on disc tribometer, you have the ball in contact with your surface. We put, of course, a control amount of lubricant on the surface, and then the tribometer so starts to rotate, and after a certain number of laps, so the friction coefficient is what we observe here increases. That means that we broke the lubricant layer. And in case of the line-like structure, we even see that the unstructured surface was performing even better. So this is not the topography in this case for enhancing the lubricant lifetime, but when we do kind of periodic dot-like or crater-like geometries, in case of the structure that were deeper, we already reach an improvement of 150%. And in case of the cross-like topographies, the improvement was even higher, significantly higher, about 1,500%. When we were doing this experiment was for a long time. I was still PhD student. I had my colleague in Spain. Now he's living in Uruguay. And for the first tests, so after some hours, the lubricant coating, let's say, was broken. But in the last surfaces, the tribometer was running even 1 week. And we're talking every day and say, no, they're still working. So we were really, really happy about this enhancement of the lubricant lifetime. So now let's go to other examples. So now is what we call, or is called, structural colors. And for the people that maybe are not so young, we have seen a CD in our life or a DVD. And we know that, for example, when we have a repetitive structure and the structure size is similar to the wavelength of the visible light, white light decomposes into a rainbow, and you see what we call rainbow colors. So, and this is what happens. I mean, we can explain it physically. So if there is a periodic structure, and here we have some white light, we have here the observer that is looking the surface, but depending on the position, there is a different observation angle, and because this different observation angle, then the observer, this person, sees the rainbow. That means we can, for example, start with a specific period, then we keep the geometry and size of the structure constant, and because we have a perfect periodic structure, you will see the rainbow color. So you can do that for create motifs, you can combine different periods, different geometries, and you can then start to create such a complex motif. But after some time, we were discussing, okay, what if we would like to have a surface that is everywhere red or everywhere orange or green and so on. And the hardware is in this picture, so we have to produce here something different. Therefore, we come now to this solution. Now we have structures that they have a variable structure period. And because now we change the structure period, if we make this calculation for a certain observation position, let's say, we can also create topographies where the observer will see under different angles the same color. And this is what it looks like, again, on stainless steel. So now we have from the top to the bottom structures that are different. So we are changing the size of the periodic structure. And once you control that, of course, then you can start to do some more funny, let's say, elements directly on the surface of a metal. Here, one more example. This is my favorite example. I would call it the rainbow without the rainbow color. This is again on stainless steel. Here, there are two things that are interesting or different. Okay, one is the black color. This is actually quite easy. You just don't have to treat at that position the surface, or it will look darker. But the other thing that is very interesting is here we observe white. And actually, if we decompose a color, we can never get white. So why we observe white? Because here we produce three different topographies. One is producing blue light, the other one red, and the other one green. And when you combine the three different wavelengths, like in a monitor, then you can also mix colors and obtain white light. So finally, here are some videos of animations, because you can also make animated images, as you can see here now in the screen. Okay, so now let's go a little to the technological part. So I mentioned that we focus on basic research, how to make these functionalities, but also how to bring this to industry. For a long time ago, so I make my PhD at the University of Saarland, and there I learned about interference structuring and the supervision at that time of Frank Mucklich. And we were using these kind of configurations in the lab. So that means we have a laser source, and we have some mirrors, and here we have beam splitter. So which means that here some part of the radiation gets through this optical element, and then we have more mirrors, and we can put everything together then onto a 3D part and create this kind of periodic lines, for instance, on a metal. But of course, this works very well in the lab, but you cannot put it into a professional system, let's say. And then when I moved later to Dresden in 2008 was that. So in 2009, we started to develop solutions for interference patterning. So the first was try to put everything into a black box, let's say. And you see here a real video of the structuring of polyimide. You see that the beam diameter on the surface is quite large. It's about 1 centimeter in diameter. You can see also that we have low repetition rate. Laser source was 10 hertz. And okay, at the end, we could create such kind of topography, but this was still not good enough for industrial applications. So therefore, in 2012, we came with some ideas with Teja Roch and Dimitri Benke, and we developed now optics that can even be combined with scanner systems, or also optics where you can translate, let's say, the part. So here you see an example, real-time video of structuring of stainless steel parts. We also started to think on replication methods, in particular when thinking to treat polymer surfaces, for example, roll-to-roll hot embossing systems. So this is a machine we developed at TU Dresden, so to treat these cylindrical tools that they are up to 600 millimeter in length, 300 millimeters in diameter also. So the area now we are processing here is called a slip. So you see rainbow color. This is the treated area. So now you see the full cylinder or slip that was treated. And then we can bring this into roll-to-roll equipment. So you see an example of a structured cylinder with some decorative elements, and here in between, I hope you can see the polymer foil that is going through these two cylinders. So now the process is getting a little faster. So we heat up the cylinders up to about 60, 80 degrees Celsius degrees, depending on the polymer material. And then we can move the foil, let's say, up to 50 meters per minute. And if we think about that the foils are about 300 millimeter in width, this is a throughput of close to 15 square meters per minute. This is how it looks, structured polymer foil after this treatment. And this foil that you see now is, for instance, interesting for application in organic solar cell or perovskite solar cells, so organic or this is not the same. You can enhance the performance. Here is 18% enhancement in the best case. And also the same topography is very interesting for reducing the addition of bacteria. So we can have polymer foils where the contamination, let's say, is reduced. And this could be, for instance, very interesting in the food industry. So now let me try to finish with a few more examples. And these are the last development of, let's say, the last 2 years. One was within the frame of the European project called LAMPAS, where we, for the first time worldwide, we combined polygon scanner system with interference structuring unit. So the advantage of polygon scanners is that they are 10 to 100 times faster than conventional galvanometer scanners. So we have here scan speeds, let's say, starting from 100 meters per second. So you can really go very fast on the surface of a material. And in this case here, we, for a relative large spatial period, so I want to say that, so 21 micron, we process here a polymer surface, creating these lines at throughputs close to or a little higher than 1 square meter per minute. It was the first time that it was demonstrated, but with a large period. So within the frame of the LAMPAS project that I mentioned before, funded by the European Union, then we developed a totally new and different polygon scanner system that today is available, but NextScan technologies that now actually belongs to ScanLab. And so we could further decrease the period to only 7 micrometers, which is the size that we need to reproduce many of the topographies I was mentioning before. The next big improvement in the technology was the development of new optics, what we call X-DLIP optics. And they have the advantage that they have a depth of focus of about 10 millimeters. This is very important because you can see here, this is a surface about 1/2 by 1/2 meter in size. So we are producing the periodic topographies on these large areas without the need to move, let's say, or control the position of the head or the distance between the head and the surface. Because within a 10 millimeters of size, we are producing more or less the same periodic structure. So this make the processing for large surfaces much easier. Before we have depth of focus shorter than 1 millimeter, maybe 150, 200 micrometers. So it was a huge improvement. And this also allow us, okay, here you can see the treatment of large areas. This case was with nanosecond pulse laser source. These optics work also with picosecond pulses, with femtosecond pulses. And again, because of this very long depth of focus, we are now able to put a laser together with a new optics into a robot arm, and now we can process without any problem also three-dimensional parts. So maybe you're wondering why you are putting the laser into the robot and you are not using a fiber, because not every laser that is available in the market can be used for interference patterning. We need some certain properties of the laser radiation that is emitted. Therefore, in this project, that is a national German project, together with Edgewave and Allotech, we started to develop this technology and bringing this into a robot arm also for the first time in the case of metals and large parts. Okay, the last is what we are doing now. Is, here I would like just to introduce the Glasgow project that started a couple of months ago. And so you see in the center of the screen, this is a machine that we are going to construct. It will combine two laser technologies, laser polishing and laser structuring using interference patterning. And the idea is to functionalize directly parts that are coming out from additive manufacturing processes. So you know that the surface topography in general of additive manufactured parts, I mean the roughness, the initial roughness is quite high. You always need to do some treatment in order to reduce this roughness. And we want to do that with laser polishing. And then on top of that, to create the special functionalities that we want using interference patterning and this microstructuring technology. Okay, so that was what I wanted to tell you today. I hope I could bring to you the importance of microfabrication method for the functionalization of surfaces, and also that some cases hierarchical is better, so that is interesting to play with different sizes of topographies. So thanks.
Thank you very much, Andres. What a talk! There's plenty of questions for me for later, but we'll see how many we get from the audience in a moment. So what we'll do now is let's bring our speaker from Pulsate on stage, Dr. Pratik Shukla, who will be giving a talk about Pulsate. Okay, so let me bring those slides up for you, Pratik. Sorry. There we go. Okay.
Thank you very much, Sam.
Thank you.
It was a great presentation, Andrea. This is just a quick snapshot of what Pulsate is, as it's responsible for supporting this event. So I'm Pratik Shukla. I am from the Manufacturing Technology Centre in the UK, and my organisation is part of this project called Pulsate that's supporting pan-European network for laser-based advanced additive manufacturing. So just to give you a quick background about the MTC, the Manufacturing Technology Centre in the UK, Coventry, was established in 2011, supported by founder universities, namely University of Birmingham, Loughborough University, the University of Nottingham, and the TWI. So it's a independent research technology organisation that's supporting growth in manufacturing, new ideas, new technologies, and taking technologies that's often die in between the fundamental science and higher TRLs to market. So the MTC sort of pick up those technologies and help to commercialize and take it to market and work with industry and academic partners. The MTC also provide training and skills development as well. So just to give you a quick background about myself, I've been involved with laser processing for a number of years. and some of my core activities lie in surface engineering, and central to that is laser shock peening. So I've been for a number of years involved in development of laser shock peening systems as well as process development. I'm also an editor-in-chief of a journal called the International Journal of Peening Science and Technology that was established in 2015. And I'm also a founder director of a company called Bright Beams Laser Technology that is commercializing portable laser shock processing systems. So back to Pulsate. So the Pulsate is a project, obviously, involving a number of partners to promote laser based advanced additive manufacturing. So these are some of the partners. Eamon in Spain are leading this project, and other partners include Sintef in Norway, CEA in France, Fraunhofer in Germany, Center for Physical Sciences and Technology in Lithuania, the MTC in the UK, which is where I'm based, the Funding Box, EPIC at Claygo. So the latter three are supporting managing the funds as well as some of the marketing. So all these partners got together to bid for the European Union Horizon 2020 program some years ago, which is where the core of the funding is coming from. So what is Pulsate? Well, Pulsate is fostering pan-European collaboration to help SMEs to grow their capabilities in the area of laser-based additive manufacturing. So new technologies coming through can be supported, funded in form of technical advice, guidance, as well as financial support to take them, enable them to go to to form a route to market and reach the end users. So it covers a wide range of areas. So it's not just limited to what's there on the screen in terms of aerospace, medical, industrial machinery, textiles, and automotive, as well as customized electronics. But these are the core areas, and the idea is to implement laser-based additive or advanced additive manufacturing in these markets and beyond that, to address challenges, burning challenges in some of these sectors that you can see. So Pulsate has been involved with what's listed there. So some of these, include, for example, welding for the aerospace sector, anti ice surfaces, from creating those from within the aerospace sector, and likewise for other sectors. So it's the scope is quite big and broad. So in the end, the final product that Pulsate may create is a digital agora, digital platform called Pulsate Digital Agora, where stakeholders, industrial partners, technology providers that are involved now, and new partners could eventually, populate this base with enough information, data that could lead to collaborative partnerships like matchmaking, for example. Also have educational material for laser users. It could also form as a advertisement or a promotion tool for new technologies that have been associated in the sector, as well as the companies that were involved with Pulsate, as well as any potential funding opportunities that may arise. So there's memberships for a wide range of people. So you could be a stakeholder, you could be a seller, you could be an educational institute, and there are stages of membership. So from free membership all the way to silver, gold, and platinum, where with respect to memberships, there may be changes in cost, and as return there is different benefits to that. So one can contribute to this platform moving forward, and make it a base for laser end users to benefit from. So in the past, Pulsate has funded various projects where new technologies were were proposed. So technology adopters and end users usually come together. And in the past, there's been funding of up to 25k for individual projects or companies that were developing new projects. And from there were many success stories, and I can give you an example of a few. So success story in terms of a project called Suba Scale Up. It was scaling up a biomimetic anti-reflective surface coating using laser surface structuring on glass, and they were as a result they were able to obtain or reduced reflectivity less than 1% on visible and near infrared um, light light sources. Another one was a project called WeldShape that was commercializing or developing a laser welding technology for hard to weld aluminium alloys, and it was a laser head that was integral with other technologies, supported by some digital and artificial intelligence driven technology to weld hard to or crack sensitive aluminium, so they were able to get good results and make the technology more integral to other technologies and scan heads and laser sources. So that's again work in progress, but some good results have been obtained through that. And the last one on the list is a project called Loom State, and that's in the garments industry, where they were sort of using laser cutting technology and smart nesting techniques to reduce the material waste, reduce the maintenance of their existing technology that they were using, which was contact based, save material and get closer to net zero, as well as reduce the carbon footprint and the waste in their production system. So that's again something that they'll be implementing as a regular production process moving forward for making garments. So at present, a bit of a short notice, but we've been advertising this for a number of number of weeks. So there's a funding call that's actually due in on the 30th of June. So very short notice, but it supports laser technology adopters and end users to come together to be funded 25k to develop another set of technology within the area of laser based advanced additive manufacturing. So if anybody's interested, please explore this. You can pick up details of the call and some of the content from any one of these domains on Pulsate, or if you want to know more, feel free to also write to me, and I can sort of guide and advise you on what may be needed to, not just for the call, but also for Pulsate as a whole. So that was, short and sweet. I'll stop there, and thank you all for listening.
All right, thank you very much, Pratik. I mean, a lot of offerings from Pulsate, and good to see those success stories of things that have fully made it to market. So I think at this point here, let's address some of the questions that we've received. So we have 3 in the chat. Before I do that, let me just release the attendance certificate link, which will pop up in the bottom left. So please do go ahead and click that. If you would like an attendance certificate for this event, this will only be available in this session. So please do click it now, but don't leave. Come back. We still have some questions to deal with. So the first of which is from Ulrika, who I think is referring to the texturing and lubrication section of your talk, Andres.
Yep.
And she asked, what would the effect of load be in EX3? I think example 3, the red friction trace, possibly. I don't know whether you would like to reshare your slides to go back to that slide.
Let's try. I imagine it's related to the cross-like geometry we observe.
I think so.
In the case of the lubricant enhancement, and I will try to show you again the screen, and I hope I hope you can see it now. Okay, so this one here. So I'm not really sure what you mean with the load here is the force over the surface. We were using loads that are comparable to what you have in motors. And the idea is to keep the lubricant on the surface so that the surface is not damaged. So I don't know if that's the answer.
Yeah, I wonder whether she just means how sort of susceptible to damage are the structured surfaces, with respect to load. That might be.
Yeah, they are clearly they have some damage after a certain time. This was something we did about 15 years ago. Now, for instance, we are also processing diamond-like coatings, that they have much better topographical, hardness and resistance to wear. And even exactly today, a couple of hours ago, we have the difference of a PhD where we structure DLC coated piston rings. And we can say that at least up to 50,000 kilometers, let's say, we observe some wear, but the structures were still there. And there was an important improvement of the performance of the motor by using the method.
Very, very interesting indeed. I was possibly going to ask about coatings and perhaps DLC, as that's something I've worked in quite a bit, so it tends to feature in a lot of my questions. But let's continue with audience questions. So we have one from Matthias here, who says, "Say I want to make the surface of a steel part super hydrophobic. What would be a good way to figure out what fabrication method is the best to go with? And following up with, how much surface area can I texture realistically in a production environment?
Yeah.
Say nanometer or micron features on 1 by 1 meter."
Okay. So the last machine I showed, that can actually process 1 meter by half a meter. So we are close to 1 by 1 meter, but this is just only a limitation of in that case, of the stages that we are using. So to make 1 square meter is not a problem. Then regarding now the super hydrophobic property, something that I didn't show very deeply, but on many of the periodic structure we use with interference, because we in some cases by using picosecond pulses, we also have the lips decorating these structures. So if we are thinking of long-term performance, I would go to picosecond processing and then using the equipment I showed before. Because of the size, it's good to have this very long depth of focus. So that is the way I would go.
Okay, great, thank you. And a question here from Mulligata, who asks, what kind of morphological characterization techniques can be used for the 4 types of textures discussed in the first few slides?
Okay, I imagine we are talking about, I don't know, in the 4 type of texture discussed around, I probably imagine there are these ones here, yeah?
I believe so.
Okay, so I try to start this. Okay, so if we just want to look the topography, what we are using in general is confocal microscopy or white light interferometer. Why? Because, for example, in confocal microscopy, if you have a 150 magnification objective, you reach a lateral resolution in the measurement of 140 nanometers, so it's quite a lot. And the vertical resolution is 2 nanometers. So structures that are, let's say, bigger than 1-2 microns, you can reproduce them very, very, very well, and also get information in a few seconds. If you want to go now deeply, for example, to characterize small lips structures, then some of them you can still reproduce them, let's say, with the methods I was mentioning before, but if not, then you have to go to atomic force microscopy if you want to really have high precision measurement. There, the lateral resolution is, I think, 0.1 nanometer, and vertical even better. So that's what I would recommend.
Okay, thank you. And question from Simpson here that I think we'll take as the last question, as we're just over an hour now. Yes, how about the shape, consistency, and repeatability of microfeature fabrication using laser methods?
That's actually a great question, because of course, we are thinking on production, we have to assure a certain reproducibility of the results. And actually, that's something that can be very well controlled by choosing the correct process parameters, for instance, in terms of the overlaps between the different pulses that we are using. So we can assure for some topographies homogeneities over 95%. That means they are very, very similar everywhere on the surface. But let me also give the last comment. In many applications, you don't need to have an exactly perfect topography. Let's say 1 micron height plus minus 5 nanometers. No, as you will see in the natural examples I was showing at the beginning, you have some range of sizes where you still have a good performance of the function. So therefore, that is even in many cases not so critical. So you can get a good performance even having surfaces that are not perfectly homogeneous everywhere.
Okay, thank you very much. So I think with that, we'll draw on into questions, although I'm sure the discussion could go on for quite some time if we let it. And we'll bring the webinar to a close here. So I'd just like to say thank you very much to the audience for such great questions. Andres, thank you for that fascinating presentation. Certainly lots to think about, and lots of papers to go look at and read further. Thank you very much, Pratik, for the presentation about Pulsate. And if anyone is interested in that, please do get in touch if you're interested in laser methods. Before we end, and if you want any more information, please do check out the handout from Pulsate, and also the link to the Pulsate website that we have. So as we draw to an end, I'd just like to say thank you from us here at Surface Ventures. Please do visit our website shown on screen, surfaceventures.org, for a bit more information about upcoming events, and you can view recordings of our past events. For our next keynote, this will be on the 27th of July at 4 p.m. British Summer Time. We'll bring the link up for that now. The website will be updated later. So please do stay tuned to that, our emails and LinkedIn posts. We also have our fortnightly newsletter, Modern Surface. If you've signed up to our mailing list, you get that. And finally, just to ask, if you found this useful, please do take the time to advertise it to your colleagues. It's always nice to sort of spread the word about our events. And with that, thank you very much for joining us today. All right.
Thanks.
Thank you very much.
Thank you. Goodbye,
Bye-bye.
everyone.
Bye-bye.
Bye-bye.
Bye.